Hello, today I'm going to talk about on-prem networking for OpenShift. First, we'll just start off with a high-level overview of some of the problems that we had to solve for this, and then we'll get into some details about the solutions we came up with for those. So to begin with, in comparison to the cloud platforms, we have no load balancer service available, we have no DNS service available. Because of the fact that we don't necessarily have automation with external infrastructure, we want to minimize the external infrastructure dependencies. We don't want to have a ton of changes that are required in the environment where you're deploying. And we also tend to run into network layouts that are a lot more complex than you might see in a normal cloud deployment. They tend to be fairly flat networks and, relatively small number of NICs. Bare metal, we get a lot of NICs and some kind of crazy network layouts, so we need to deal with that as well. So some of the high-level solutions: we host a load balancer in the cluster, we host DNS in the cluster. We've done everything we can do to minimize the infrastructure requirements, and I'll talk a little bit more about exactly how we did that later. And then we also have some advanced network configuration tools that are present both at deployment time and also post-deployment. Just some general implementation notes for the on-prem networking services. Most of them are static pods that are deployed by Machine-Config-Operator along with some configuration files and systemd services. There is some additional config templating that happens with bare metal runtime config, and that's to handle things that are, say, machine-specific, because Machine-Config-Operator can't do machine-specific details. We also have NMState integration into the bare metal deployment process and the Kubernetes-NMState Operator for day 2 networking configuration. So first we'll talk about the cluster-hosted load balancer, and that is implemented using keepalive and HA proxy. So we have two virtual IPs. One is for the API traffic and one is for ingress traffic. Then for the API, we use HA proxy to distribute the API traffic to the available API servers. Ingress traffic is already distributed by the router pods, so we don't need HA proxy there. It would be redundant. The API VIP is only configured on control plane nodes because that's the only place that the API servers are running. And the ingress VIP can be configured to run on either control plane or workers. It's going to prefer whichever nodes are running the default ingress router pods. And we'll talk a little bit more about how that works later because there are some subtleties. But it can live in either place. It will usually live in one or the other because you wouldn't typically run that in both places. So a few more details about this implementation. VIP failovers will cause existing connections to break, so those are something we really want to avoid. Technically, that's not even allowed in the OpenShift architecture, but this was the best we could do. So what we do is we try to limit the VIP failovers as much as possible, and to do that, we have keepalive set up to leave the VIP on a node unless the HA proxy on that node stops working. And what that means is that if an API server goes down or a node needs to be rebooted or something like that, the VIP doesn't necessarily fail over just because of that one outage. It will only fail over if the node that is hosting the VIP either has to go down or if HA proxy quits working for some reason, which is unusual, but you never know. Additionally, the health checks are timed so that HA proxy is going to handle outages before keepalive notices them. So you can see the snippets from the config down here, and the interval on the keepalive health checks is 2, so that will run every 2 seconds, and the fall value is 2, which means that it has to fail twice before keepalive will trigger a failover. And then you can see in HA proxy our interval is 1 second with a fall of 2. So HA proxy is going to notice an outage on an API server in about 2 seconds, which is only one of the health checks from keepalive. So in theory, the keepalive health check should be healthy again by the time it runs for the second time, because HA proxy will have noticed the outage and removed the master from the backend list, and so the next time keepalive tries to talk to it, it will be working. This is just a diagram of the load balancer traffic flow for API, And you can kind of see from the arrows here how things are arranged. So we have the 3 keepable IDs on the masters, and they're managing the API VIP, which kind of exists outside of any single master. And so in this example, we're assuming that the API VIP is on master 0. So you can see traffic comes into the API VIP. It goes down to this IP tables rule that is moving port 6443 to 9445, only for traffic that is coming into the API.cluster domain DNS name. And the reason we do that is because HA proxy is actually running on that second port, and then that is what distributes the traffic to the different API servers. Now, the important thing here is that because that only handles traffic to the DNS name, communication between the API servers does not go through any of these intermediate steps here. So the API servers are able to talk directly to each other, but any traffic that's coming in through the API VIP should be going through HA proxy and getting load balanced. We have a little bit simpler diagram for ingress because, again, no HA proxy, so no IP tables rule and no extra service there. The main thing to note here is that you can have the ingress routers running on the masters. You might do that in a remote worker scenario because keepable can't work across subnets, and we'll talk a little bit more about that later. So in that case, you might have the ingress VIP on your masters. By default, it would live on your workers, and you can see that here we have the worker keepable ID that manages the ingress VIP, and then traffic comes in, goes to the default ingress router, and then it gets distributed to the various backend services. The other thing to notice here is the shard ingress router. It is possible to be running multiple ingress services, and we want to be using only the default one because the ingress VIP needs to be providing access to things like auth and console that may not be running in the sharded environment. Another thing that's a little bit complicated with this is how the API VIP behaves during Bootstrap. So what's going to happen first is that keepable will start on the Bootstrap node, and it will take the API VIP because it's the only node that's running. The Bootstrap keepable though, also has the highest priority configured of any of the nodes, so it's always going to take precedence over the cluster nodes. And so that means that the API VIP is going to stay on the Bootstrap node as long as possible. Then bootstrapping is going to happen, and the Bootstrap control plane will get torn down, and so the Bootstrap API server is going to be gone. Keepable monitor will notice that and will stop keepable on the Bootstrap node. And what that will do is allow the VIP then to move to the cluster nodes and become part of the cluster, and the 3 masters will negotiate amongst themselves and figure out who needs to take the API VIP, and then the Bootstrap will be out of the picture. It is worth noting that sometimes the Bootstrap keepable will stop before bootstrapping is complete, and that's because the API server will bounce up and down a little bit during bootstrapping. What will happen in that case is that once the API server comes back up on the Bootstrap node, keepable will also be restarted, and then it will take the VIP back because, again, it has the higher priority. Okay, and we already covered all of that. So there are some limitations to this architecture, as you may have seen. For one thing, all of the traffic is routed through a single node. At least all of the API traffic and all of the ingress traffic goes to a single node, whatever is holding the VIP. So that's a potential scalability issue. Again, the processing doesn't necessarily all happen on one node, but all of the network traffic for API and ingressors is going to go through one node. And so that's definitely a concern. So to mitigate that, we do support configuration of external load balancers, and basically what that would be is maybe you set up an F5 box on your network and send all of your DNS records to that, and then that will handle the load balancing to your cluster nodes. This is very common, again, in bare metal situations where a lot of times there's already some load balancing infrastructure in place, but it's not the kind of automated load balancing that we would see in a cloud environment. So we can't necessarily programmatically use the existing load balancer, but it is something that can be configured after deployment and used to get around some of these limitations. I will note that in the external load balancer case, the internal cluster traffic does still go to the internal load balancer. This is because it just turned out to be very complicated to try to switch the internal traffic from internal to external and have it still work on scale out and all of that sort of thing. So for the moment, we're just leaving internal traffic on the internal load balancer. If it ever becomes a problem, then we may have to revisit that, but it turned out that it was a lot safer to just leave it alone. We're also considering trying to use Metal LB as a possible future replacement for the cluster-hosted load balancer. This would move some of the load balancing out of the cluster and into the network infrastructure of the environment. And so that would be really, really good. Unfortunately, it has a bootstrapping problem because you need to have the cluster up before you can deploy Metal LB and start using it. So it doesn't really work for the initial deployment. Obviously, there are possible solutions to that, like just using the internal load balancer until Metal LB can be deployed. But we're still thinking about exactly how we want that to work, and so that's definitely future work. In addition, currently dual stack clusters only have IPv4 VIPs, and that's because IPv4 is the primary IP version on dual stack clusters for us, and that's a broader OpenShift limitation, not specific to on-prem. We do plan to fix that in 4.11 and add proper support for both dual stack IPv4 and IPv6 VIPs. When we initially did this, we only had single stack support when this was first implemented, so wasn't considered that we might need two VIPs. And also, when we did add dual stack support, it was assumed that all of the cluster nodes would have access to both IP versions anyway, so it didn't really matter if the VIPs were only one or the other. Unfortunately, it turns out that customers were running IPv6 single stack applications on their dual stack clusters, and then those did not have access to API or ingress because they couldn't get to the IPv4 VIPs. So as I mentioned, planning to fix this in 4.11. There's also a workaround available that we can use to add IPv6 VIPs. It's a little bit manual and not as easy to support, so it's not something we can really include in the product right now, but it is available if customers run into this in an older version and absolutely must have dual VIPs. As I mentioned before, in remote worker scenarios, we can't leave the ingress pods on the workers because then KeepAliveD is going to have to try to work across subnets, and that just doesn't work. So what actually happens is that you remove KeepAliveD from all of your workers and you switch your ingress to run on the masters, and then since the masters all have to be on the same subnet, and that's again a broader OpenShift design constraint, we don't have to worry about the cross L2 traffic with KeepAliveD, and your ingress works as you expect. So then moving on to cluster-hosted DNS. This is a static core DNS pod that runs on every node in the cluster, and core DNS is the same thing that provides the cluster DNS from the DNS operator. We have a network manager dispatcher script that is set up to prepend the local IP address to resolve.conf so that we're always using this local core DNS before any other configured DNS servers. And then our core DNS is configured to forward traffic to the upstream DNS servers as needed. So some things to note about this. Network Manager is configured not to manage resolve.conf at all. If our dispatcher script doesn't populate resolve.conf, it doesn't get populated. So if you see a node without a resolve.conf, it may have been a problem with the dispatcher script. And also, we do prepend the actual node address, not just localhost. And the reason that we have to do that is that the resolve.conf from the host sometimes ends up in pods that are namespaced, and as a result, they don't have access to the actual local host. And so if they try to just talk to our DNS server on localhost, they won't get to it. Whereas if they use the actual node IP, then the traffic flows correctly. So there's a little bit of logic in the dispatcher script to handle that, and that's why that's there. So the API int record is one that's required for all OpenShift clusters. It's how the cluster kind of talks to itself, and so that is provided by this core DNS. It's just the API load balancer VIP, and that is templated in by machine config operator because MCO has access to the configuration data that tells us what the VIP is. We also provide API and ingress records, the wildcard for ingress, and that was done primarily for POC deployments. We can't recommend this for production just because obviously it makes the cluster inaccessible from external sources. You would have to point all of your clients at the cluster DNS servers in order to resolve those names. So this was just there to allow customers to deploy without any DNS changes in their environment, because we know that sometimes that can be kind of a hassle to get those approved and implemented. So this allows you to point your provisioning node at the API VIP for DNS, and then it will be able to pick up these addresses and talk to the cluster. Again, not a supportable thing. We would not. I don't even know if we would give a support exception for this because it's really not intended to be used in production. It's just to help you stand up a cluster with little to no external changes. We also provide through this local DNS server node name resolution so that each one of the nodes can look the other nodes up by name. So master 0 can ping master 1 by name. That is handled now by the core DNS monitor container and the host plugin in core DNS, and the monitor just templates in the addresses of all of the other nodes into the core DNS configuration, and it gets that list from the API, so it should always be fairly up to date, at least between when a node gets added and when it gets noticed by the monitor. We did previously use core DNS, MDNS, and MDNS Publisher for node name resolution. That turned out to be a problem because multicast is not allowed in some environments, and it in some cases for very good reason, because it was also a scaling issue because the large amount of multicast traffic that started getting sent around in larger clusters was actually overwhelming network interfaces. So we did move away from that, but that is something that is still present in some older releases, so if you run across that, that is why. So here we're just looking at some snippets from the on-prem core DNS configuration. So you can see we put the upstream DNS servers in the forward plugin, and there may be multiple addresses here. In this case, the cluster only had a single upstream DNS server, but if there were multiple addresses, we set the forward policy to sequential so that it works kind of the same as the operating system DNS resolution would. If we don't set it to sequential, core DNS actually defaults to round robin, I believe, and then what happens is you'll have a resolve.conf configuration that works fine, but when you add it to the forward configuration, all of a sudden we start using all of the servers in resolve.conf, and if it turns out that the second or third server in that list didn't actually work, all of a sudden your DNS requests start to fail, and it looks like it's a problem with core DNS, and it's actually a problem with your DNS server, but this way we don't get blamed for it because our DNS forwarding works the same as bare resolve.conf would. Then we have these kind of complicated looking template plugins down here, and these are used for the API int and API and ingress records. And the reason that we do this is because the host plugin actually doesn't have RFC compliant behavior for IPv4 and IPv6 records, and so by providing these two separate templates for those, we're able to provide RFC compliant behavior without having to actually modify core DNS to do the right thing, although that would be a nice upstream contribution if we could do that. But in the meantime, we're using these templates, and so that's why this looks a little bit complicated, is because we're kind of working around a limitation of core DNS there. And then down here you can see just the host list. This is all templated by the core DNS monitor, and everything has the fall through directive on it, so that if anything doesn't match one of our internal records, it will just get forwarded on to the upstream DNS servers. One other thing that we ended up having to deal with in on-prem and actually some non-on-prem deployments was node IP selection. It turns out that Kubelet's node IP selection logic is not super consistent or robust. So one of the things that we implemented in the bare metal runtime config project is node IP selection, and this gets used for the on-prem and UPI deployments. And so essentially what it does is on platforms that use VIPs, which is the on-prem platforms, it's going to select an IP from the same subnet as the VIP. So it's going to go out, look at the VIP, and then go find an interface on the node that has an address that is in the same subnet as the VIP. If it cannot do that, either because there is no VIP and this is a UPI deployment, or because this is a remote worker on a VIP-based platform, but it's on a different subnet, so it doesn't actually have an interface that matches the VIP, then it's going to fall back to using the address associated with the interface of the default route. And if there are multiple default routes, it picks the one that has the highest priority. And then I think there was another criteria, maybe based on IPv4 and IPv6. So there's some logic to select a consistent and hopefully correct node IP. Now, it turns out that this is not always the behavior that deployers wanted. Some of them were actually relying on the slightly flaky kubelet behavior before. And so when we implemented this logic, it actually broke a few people. Not nearly as many as it fixed, but it kind of left us in a weird place because we had fixed a bug, but it also broke a handful of customers. So in 4.11, we've added this kubelet node IP hint environment file that can be added to the node IP configuration service. And then that can be used in UPI deployments to override the default logic for the selecting the default route interface. Essentially what happens is the IP provided in the hint is going to be treated the same way as a VIP, and so it allows you to essentially tell the node IP configuration service which interface you want to select the IP from. We're most likely going to backport this to older releases than 4.11 because this goes back to 4.5 or 4.6, and we want to help out the people who are deploying on those older releases as well. There is a workaround for this, but it's really ugly if you don't have this new hint file. And so we really want to get this into all of the releases that we can, just to make that user experience much better. So as we talked about, there are some external infrastructure requirements when you're deploying on-prem, and they're pretty minimal. You can see right here, it's just the 2 DNS records, one for API and one wildcard for the ingress. And then you'll need to have DHCP reservations for each node. We'll talk about why this is optional in 4.10 in a moment, but that is important because OpenShift does not support changing node IPs without completely redeploying the node. So you really need to have your DHCP reservations set so that when DHCP leases expire, a node doesn't go out and request a new one and then somehow get back a different address. So there are exceptions. We can actually do deployments without either one of those bullet points. You can deploy, as I mentioned earlier, without API and ingress records in your external DNS. You do that by pointing your provisioning node DNS resolver at the API VIP, and then that will use the internal core DNS server that is providing all of the internal DNS records to the cluster. You'll be able to take advantage of that as well. Again, this is not supported for production. It's just to do proof of concept deployments and maybe to get a cluster stood up before you're able to get the DNS changes made in your external infrastructure. You can also do deployments without DHCP reservations. Obviously, the initial deployment is going to work fine in that case. The danger with that is, again, if your IPs change when your DHCP leases expire, then you may have a problem. In 4.10, we also added the ability to do static IP configuration, and that's a bare metal specific feature that doesn't work for any of the other platforms, but at least on bare metal you're able to deploy with static IPs, and obviously in that case you don't need any DHCP infrastructure at all, which is one of the main drivers behind static IPs. And the second bullet point there is just talking about the fact that you can deploy without the reservations in the first place. However, if you do stand up a production cluster that way, you need to go in after the fact and create the reservations so that your node IPs are not going to change on lease renewal. And provision time networking is actually the thing that provided the static IP support. So we'll talk about this real quickly. This is also frequently known as day one networking, which is a bit of a misnomer. But if you hear someone talk about day one networking, this is probably what they're talking about. I'll try to use the provision time terminology here, but if I slip up, that's what I mean. So in bare metal, a lot of times deployers are wanting to use networking layouts that are a little bit more complicated than what you would typically see in the cloud. A lot of them want bonds for increased throughput and redundancy. They want VLANs for better network segmentation. They want static IPs so that they have less external infrastructure. And there are plenty of other things that are going on in bare metal environments that maybe don't show up as much in the cloud. Some of these configurations can be done with machine-config operator, just laying down network connection files in the host. However, not all of them can be. For example, some bond modes don't work if you've only got one of the interfaces up. So in some cases, you can bring a bond up with just the one interface and get your cluster created, and then create the bond after the fact. That doesn't work with every bond mode, and in some cases, our customers want to use the bond modes where that doesn't work. VLANs are similar. Obviously, if you're required to use a VLAN to talk on a particular switch port, you're not going to be able to get out to join the cluster until that VLAN is configured, and so you can't use MCO because MCO isn't there yet on the initial deployment. Yeah, a little bit different problem with static IPs, specifically that they require per node configuration, and MCO just doesn't support that. You also have the chicken and egg problem of it has to be able to get out to get the MCO data to apply to the node. So static IPs really were one of the biggest things for this feature, because without provision time networking, you just couldn't do this. These are not exclusive to bare metal, and we do want to apply this functionality to the other platforms, but in this case the implementation was bare metal specific because we're taking advantage of the metal IPI deployment process to do this. And so right now this is bare metal specific. We do have longer term plans to add it to some of the other platforms as well, though. And I should mention, some of these things, the bonds and VLANs especially, some of them were implemented using custom images previously, and that does work. It's a little bit more of a hassle. In fact, the implementation of provision time networking was very much just a bit of automation around the custom images, because that's essentially how we're doing this is custom images. And that couldn't do static IPs because the custom images couldn't be applied per node, and this feature has now added the ability to do configuration on a per node basis. So it was necessary. Some of these things could be worked around before, but this is, again, also a much better user experience just all around. So the solution that we came up with was network configuration in install config. It's part of your bare metal host definition, which you already would have been doing on bare metal. And it is NMState syntax. NMState is a declarative network configuration tool that is part of the Network Manager project. And what it does is you provide an NMState configuration that gets converted to raw Network Manager NM connection files, and then those are injected into the node at deployment time with the copy network option in CoreOS install. Using NMState for this does provide us a little bit of sanity checking, because if you have a syntax error in your NMState configuration, it's going to tell you right away. You don't just have the node come up and the networking is broken and you don't have any idea why. That's a really terrible debugging situation, because a lot of times you can't even get onto the node to see what's wrong without having to go to a console. And so it's something that we really want to avoid, and NMState kind of helps us with that. The other thing that is really nice about this is that we have a day 2 configuration mechanism that is based on the NMState syntax. So you can essentially take what you pass in install config during your initial deployment and hand that to the day 2 configuration, and then if you need to make any networking changes from there, you have a solid basis and you can use the exact same configuration. This is an example node network configuration. This is an example provision time network configuration. So you can see this is the host list, and we're looking at master 0 here. There would be some other configuration options, and then you get down to this network config dictionary. And this from here on down is all NMState syntax. So interfaces, DNS resolver, and routes are NMState configuration primitives. And you can see basically what we're doing here is we're statically configuring an IP on this node, and then that means we also have to statically configure the DNS and the routes, because we can't get those things from DHCP like we otherwise would. So there are some limitations that we know about in this feature as well right now. For example, the static IP configuration has resurfaced some bugs with reverse DNS hostname lookup in Network Manager. Previously, we were getting around that by telling people to set their host names using DHCP. Obviously, in a static IP scenario, we can't do that. We've also found a few other bugs that are caused by things like the fact that we normally DHCP all the things on a node, and now that we're applying a separate connection profile for some of the interfaces, you can end up with both the default DHCP profile and the new custom profile kind of fighting over the interface, and then you end up with races, and it's kind of a mess. We do have a workaround for that, but it's something we still need a better fix for. So something to be aware of. Also, this should not be mixed with any other network configuration system. If you were previously using machine config operator to lay down network config, you should stop doing that and switch it all over to this new mechanism. Once again, you don't want to have two different tools that are trying to configure the same interfaces using different methods, because they'll conflict, and then it'll be potentially undefined which one wins and which configuration you end up with. And it's kind of redundant. So as I mentioned, some of these have workarounds, but we do need better solutions to some of them as well. The reverse DNS hostname lookup, there are some fixes in Network Manager that we just need to pull into our RCOS images. And we're also looking at some alternatives to setting the hostname using reverse DNS to take advantage again once again of our metal-specific deployment mechanisms. And then, as I mentioned, we do also have a post-deployment configuration tool, and that is the Kubernetes-NMState Operator. And what this is a declarative system for configuring networks in a Kubernetes cluster, specifically host networking. This right now is an optional component that gets installed from Operator Hub. We're hoping at some point to make it part of the default payload, because we think it's really useful, including across platforms other than bare metal or even the on-prem platforms. But we're still having those discussions, so right now it's still optional. It uses the NMState CLI tool to apply the configurations that you specify, and we looked at one of those earlier. We'll take another look at one in a moment here. Each host in the cluster is going to run a handler pod that is connected back to the operator, and essentially that pod is what is going to be responsible for applying the configuration to each node. So a lot of times that if there's an error, that's a good place to start looking, is check the logs for the handler, and many times you'll see what the error was. The handler pods do only appear after an NMState instance has been created. You just need to do that once when you install the operator, and then you'll be able to do all of your configuration after that. But that is a prerequisite to any of the pods besides the operator itself getting deployed. We ship a downstream fork that contains some OpenShift specific modifications. We have our OLM manifests for the various different OpenShift versions. We needed to add security context constraints because that's a model that only exists in OpenShift, so it doesn't make sense for the upstream project to have that, but it is required for it to work in OpenShift. And there are a few other small changes. We do try to stay as close to upstream as we can, and any changes we can make upstream first, we do. We rebase at least once per cycle so that we're keeping up to date with what upstream is doing. But we do have to use a downstream fork because there are some things that are a little bit different in the OpenShift version. A bit of history too. This operator was originally part of the CNV component, and actually right now it still is part of the CNV component. But it turned out that it has applications outside of CNV, and as a result, customers who didn't want CNV were wanting to use this operator, and so we decided to create the standalone project, and then once, and actually in 4.10, the standalone operator is becoming the officially supported GA method of doing network configuration, at least on bare metal, which is also the only platform that CNV supports. So for the moment, we're just keeping the same level of support for that. Now that it's GA, we are planning to migrate CNV users from their integrated operator over to the standalone operator. That hasn't all happened yet, but it is underway, and hopefully by a release or two for now, everyone will have been moved off onto the standalone operator, and we won't have all of that duplication anymore. So this one is an example node network configuration policy. You can see some of the kind of boilerplate stuff up here. This also works on a per host basis. So again, unlike maybe an MCO network configuration method, we are able to apply network configuration to a specific node, which again allows us to do things like static IPs on secondary interfaces or what have you. In this case, what we're looking at is an example of changing DNS settings on a node, and this was actually the #1 requested feature that led to Kubernetes-NMState becoming a part of the product. So what you can see here is we have search and server configurations, pretty basic DNS stuff, right? We do also, in this case, if we're using DHCP addressing on all of the interfaces on the node, we do also need configuration to set one of them auto DNS to false. And the reason for this is NMState needs an interface that it can apply these DNS settings to, and if all of our interfaces are dynamically configured, it doesn't have any place to store it because that may get overwritten by the DHCP values. So if you had static IPs, then obviously you don't need this part, although you have a different interface configuration in that case. But if you are using DHCP, then you'll need something like this that sets auto DNS to false. So again, there are a few limitations with this feature. It can't be used to configure the primary interface in Oven Kubernetes deployments right now, and that's because OvenK uses the configure OVS script to create a bridge on the primary interface, and as a result, we have the problem of two different tools trying to configure the same interface again. You can use it to configure any other interfaces on the node, like if you have a storage interface or something like that. Unfortunately, right now you can't use it on the primary interface. You also shouldn't combine it with machine config operator configurations for the same reason, because you don't want to have two tools configuring the same interfaces. We are hoping at some point to start using NMState to manage the Oven Kubernetes bridge. And at that point, it should be possible to do configuration of that with the operator, because it'll all be kind of in the same system. But that's probably still a ways off. It's a fairly complicated thing to do, and so we're not quite there yet. As we mentioned, DNS configuration requires either static IPs on an interface or a DHCP interface with auto DNS set to false. And another kind of historical note, in older releases, we had ephemeral network config, which meant that when the operator made changes to the networking on a node, those changes disappeared after a reboot, and that was obviously problematic for a number of reasons. They would eventually be reapplied by the operator after it came back up, but if you had made a change that, for example, you configured a VLAN or something like that where it was required for the node to come back up properly, then that was going to be a problem. So we fixed that in 4.10. Network configuration is now persistent across reboots, and so you shouldn't have to worry about that, but it might be something you would run into in an older release if you're using the tech preview version of the operator. So we have, and I've touched on this a little bit earlier, but we have a lot of future plans. There's plenty of features and bug fixes that we're looking to make as soon as possible. Some of them are obviously higher priority, and we want to get them in as in the very next release. Some of them are definitely going to be longer term plans, either because they're just really complex and not something we can do in one cycle, or some of them are just lower priority. So this is almost certainly not a complete list, but it's just a few that I came up with off the top of my head. So as I mentioned, having support for dual stack VIPs is really important. That one is one of those top priority things. It's getting all of our attention right now, and so hopefully that should make 4.11. We also want to add support for the provision time network config on all platforms, and again, that's kind of in service of replacing the much unloved configure OVS script for Oven Kubernetes. Having to try to script the bridge creation has turned out to be a real big hassle, and it's not very flexible. And when you have customers who want to do something that's kind of unusual or was unexpected by the script, it's really hard to do that. And so we're really hoping that the provision time network config can maybe replace that, and we can have the bridge created at provisioning time, and then we don't have to worry about all of the runtime configuration that configure OVS does. We've also had some discussions about doing some network validation prior to the cluster deployment. As I mentioned earlier, when your cluster nodes come up and the networking is broken, it's a really hard thing to debug a lot of times, because sometimes you don't even have access to the node, and it's a pain. So in order to try to make that at least a little bit less painful, we would like to come up with some sort of a system to kind of go out and validate that your connectivity and all of your interfaces is working correctly, and maybe we can even apply that provision time network config and just verify that everything seems to be working. Basic sanity checks, pings, and maybe some DNS lookups and that sort of thing. This is still in the very early stages. We've had a few kind of high level discussions about it. Obviously, I don't have a lot of details yet about it though, so we're looking into this. It's kind of one of those longer mid to long term plans, but I think it would be a really big improvement in the usability of OpenShift if we could get something like this in. And I know other teams agree with me, because it was actually brought up by someone else from the Metal team. So it's definitely something people are interested in. It's just a kind of a question of figuring out how to do it, and then finding the time to actually do it. And then, as mentioned earlier, we do want to integrate with the Metal LB operator to help with the stability and scalability issues with the current cluster-hosted load balancer. There are still questions about exactly what that looks like as well. So again, still kind of early days with that, but definitely something we're interested in doing now that we have the MetalLB operator kind of integrated into OpenShift. And so that's it for the presentation. If you made it all this way, thank you, and I hope it was useful and you learned something about how on-prem networking in OpenShift works. And if you have any questions, my email is in the first slide, and feel free to contact me on Slack. My short name is my Slack name, or any other way that you want to get a hold of me. I'm available to talk on-prem networking, and thanks for watching.